Traditionally, robots are capable of high speeds at the sacrifice of ultra-high precision, or are capable of ultra-high precision but at the sacrifice of speed. In order for a robot to produce large and small-scale manipulation, its actuators must be capable of high speeds and ultra-high precision simultaneously. However, the design criteria for high speed and ultra-high precision are often at odds with each other. This is because submillimetric motion steps are achieved with the use of transmissions with large speed divisions. The literature addresses multi-scale manipulation by combining a manipulator capable of macro motions carrying another manipulator that is capable of micro motions. Our work is motivated by the need for multi-scale manipulation in a single robot, particularly in light of extraocular subretinal drug delivery, where macro motions are used to position a robot with respect to the eye, and micromotion is used to inject a drug to specific subretinal layers. To address the need for multi-scale manipulation, we present a parallel robot utilizing twisted wire actuators for micromotion. We also provide a suggested methodology for selecting the parameters to design the twisted wire actuators in order to meet workspace needs, such as minimum motion resolution. In this paper, we use a planar parallel robot as a testbed to demonstrate multi-scale motion capability. The robot's moving platform is actuated by 3 Velmex linear stages used for macro motion. The Velmex slides are anchored to a base platform which incorporate flexures. These flexures are separately actuated with twisted wire actuators for microscale motion, so that when active, the macro actuators will follow a circular trajectory, with the center of rotation at the flexure. We observed the effects of twisted wire actuator parameters on the robot's motion characteristics from simulation of the instantaneous kinematics that are detailed in the paper. We consider first the translational and rotational resolutions separately. By representing joint motion as a vector in the worst-case scenario direction with a magnitude defined by the gearhead transmission ratios and encoder resolutions, we find that a minor increase in the twisted wire actuator's wire diameter has profound impacts on the minimal achievable translational resolution. We perform the same analysis for rotational resolution and draw the same conclusion on the effect of wire diameter. A similar simulation considering the mechanical uncertainty of the twisted wire actuator's driving mechanisms, where the joint motion vector is represented this time by a magnitude defined by the gearhead's backlash, also in a conservative worst-case scenario direction. The same trend with wire diameter is observed here as with motion resolution. From these simulations, we generate a generalizable instruction set to direct component selection with the goal of achieving workspace motion characteristics. This chart is a visual aid that can be used to begin component selection by observing positional uncertainty as a function of twisted wire actuator wire radius and gearhead backlash. From there, the following algorithms are used to finalize selection to meet workspace demands. The details of these algorithms are laid out in this article. We experimentally evaluate the macromotion behavior using an NDI Vicra Polaris optical tracker with a marker at the origin of the robot's moving platform and demonstrate a 10 mm diameter circle. To experimentally evaluate micromotion, we use the customized image tracking procedure shown to be accurate within 1 micron. We use a laser etch optical marker fixed to the end effector to track position using a sequence of images obtained with a microscope. We employ a variable radius model used in twisted wire actuator position estimation modeled as a polynomial and achieved an end-effector radial RMSE of 18 microns when following a 250 micron radius circle. The robot in these experiments was controlled using an inverse kinematics solution in an open loop. We achieved macro and micro motion using a weighted least squares redundancy resolution strategy. In equation 3, the entries of the weight matrix act as penalties on their corresponding joints to either selectively actuate or stop motion by decreasing or increasing their magnitudes respectively. By adjusting the magnitude of the entries of the weight matrix, we can seamlessly transition from macro motion to micro motion. Here we demonstrate the robot employing the macro actuators at the beginning of a path following task prior to reaching a preset distance from its target, where it then switches to the use of micro actuators to close positional error. Thank you to Vanderbilt University and the NIH for partially funding this project. Thank you for watching.